Okay, I have a few here that are filled out, so check to see that you had the same answers there. But let's talk through 6, 7, and 8. Number 6, did anybody get the answer to number 6? Log base 2 of 8. Maggie, what'd you get? 3, that's the correct. How did you know that?
Because
Excellent. So if we change this to log base 2 of 2 cubed, then you can see that you get that answer back as 3. Nice. How about number 7? Did anyone get number 7? Jeremiah, how'd you do it?
I put 5 as the base and then we get 1 over root 5 becomes negative 1/2 because that is the denominator.
Awesome. Awesome. So Jeremiah changed this 1 over root 5 to have this base of the log, which is 5. And he did that by, he knew that if you have a negative exponent, it puts it underneath 1. And then the 1/2 is what causes you to have that square root. So he looked at this as log base 5 of 5 to the negative 1/2. And then what'd you get as your answer? Exactly. Very nice. Okay, finally, number 8. What would be 10 raised to the log of 9? Anyone get this one? Nate.
9.
9. How'd you know that?
Because one of the special logs is just log base 10.
Excellent.
So,
Yeah, he knew that if there's no base written, it's understood to be a 10. Because this is one of the special logs. It's called a common logarithm. It's one of the buttons on your calculator that's more easily accessible. So that's just something to think through. All right, today we move into the idea of graphing logs. And the best way to begin looking at graphing logs is to think about them in terms of an inverse. So today we will see a connection between two ideas we've studied so far, inverses and then exponential and log functions. Let's remember what we know about inverses. You guys learned some of this with me, some of this on Khan Academy. So let's just remember that with an inverse, another name for inverse is opposite. So you want to think about opposites, or they undo each other. You guys remember, like, the inverse operation of multiplication is division. Inverses kind of undo each other. When you look at the graphs of inverses, go ahead and write that in. Graphs of inverses reflect around a line. Do you guys remember what line that is? Yes, reflect around the line y equals x. And the last thing that we also took a look at is that the domain becomes the range of an inverse. Becomes the range of an inverse. And the range becomes the domain. Becomes. Okay, those are just some ideas of inverses. And then let's just remember, let's do like a basic example of how do you find an inverse. So if I'm going to do this one in red here, just a basic example to help us think through the logarithm example. For example, if I had y equals 2x, or let's change that to be f of x equals 2x. Does anybody remember how to find an inverse? How to like take this function and find its inverse function? Maggie? Good, set 2x equal to y, and then we switch the x and the y, and then what would we do? Solve for y. So Linda said divide by 2, she's right. So x over 2 is equal to y, but instead of writing it as y, we would represent that as the inverse function. Okay, that's a basic example. Now let's use what we remember to develop the inverse of this exponential function. So if I have f of x equals 2 raised to the x power, let's use Maggie's method, what she reminded us of. What would we change f of x to first? Y. So we have y equals 2 raised to the x. Then what would we do? Switch the x and y, so I'm going to make y x and I'm going to make x y. And now I have x equals 2 raised to the y power. and then I have to solve for y. So just as a reminder of what we did, we switched the domain and range. We switched the x and y. But now we have to solve for y. Okay, this is going to take revisiting what we learned yesterday. How do we isolate y? How do we solve for it? Log base. So excellent, I heard logs. We change it to log form. So we would do log base 2 of what? X equals y. And now we've isolated the y. But instead of writing this as y, what could I rewrite this as? Yeah, f to the negative 1, which is your inverse function, equals log base 2 of x. So what do we notice off to the side here? An exponential function with a base of 2 has an inverse function. Well, I don't know if it's a function yet. I would want to see the vertical line test, but it does come out to be a function. But these are indeed inverses of each other. So 2 to the x has an inverse of log base 2 to the x. So we now see that a log is actually just an inverse of an exponential equation. So keeping in mind what we know about inverses, let's go ahead and let's graph both of these. So logarithms provide a way to express the inverse of exponential functions. Sketch the graph of each of the following by building XY charts. So if I'm looking at the basic graph, 2 to the x equals y, what numbers would you guys want to plug in? 0. Should we plug in some negative ones? Like negative 1, negative 2 maybe? And then 0, we'll do like 1 and 2. Is that good? Okay, so what's 2 to the negative second power? 1 over 4, good. What's 2 to the negative first power? 1 over 2. What's 2 to the 0 power? 1. What's 2 to the first power? 2. What's 2 squared? 4. So I have these ordered pairs. I have negative 2, 1/4. I have negative 1, 1/2. I have 0, 1. I have 1, 2. And I have 2, 4. And then do we remember what happens to the left of this point that I've graphed? Never touches 0. Excellent. So it gets close to 0 but never touches. In fact, I could say that this function has a horizontal asymptote at y equals 0. You guys remember that from graphing exponential functions? And then we know that this graph is going to continue exponentially, increasing. Okay, if I'm looking at log base 2 of x, well, since I know it's the inverse, let's say I start with 1/4. Think about this mentally, just so you can confirm that they really are inverses of each other. Log base 2 of 1/4, aka log base 2 of 2 to the negative second power. What should that come out to equal? Negative 2. How about 1/2? Log base 2 of 1/2 is the same as log base 2 of 2 to the negative first power. So what should come back? Negative 1, and I wanted to do this in a different color actually, because I'm going to be graphing in a different color. And if I plug in 1, what should I get back? Log base 2 of 1 would give me 0. If I plug in 2, what's log base 2 of 2? 1. And then if I plug in 4, what's log base 2 of 4? 2. So let's graph these points and see what the shape looks like. So I have the point 1/4, negative 2. I have the point 1/2. That should be a negative 1. Oh, I just marked it in a different color. 1/2, negative 1. 1, 0. 2, 1. 4, 2. And I could keep going and going and going and going. And then what's happening to all these points that are down here, the negative y values? They're getting closer and closer to the the y-axis. They're getting closer and closer to the x value of 0. Okay, so let's take a look at what would be let's take a look at the exponential function. We looked at the domain and the range of this function. What's the domain of the exponential function? What are all the possible x values that you can plug in and get real number outputs? Good. Negative infinity to infinity. What was the range of the exponential function? What's this? Yep, 0 to infinity, but I should have a parentheses around 0 going to infinity. So if I'm thinking about the logarithm graph, since it is an inverse, the domain and the range are switched. So what should be the domain of the logarithm graph? 0 to infinity. Can it ever reach 0? Nope, we can't have log of a 0. And then what would the range be? Negative infinity to infinity. Now the exponential graph had a horizontal asymptote at y equals 0. So extend that to your log graph. What would that look like? You would have an asymptote, but what would it look like? You have, yes, you have a vertical asymptote, and it would be at x equals 0. Now, just to confirm your understanding of inverses, you could go ahead and you could draw this line, y equals x. So you have points on this line like 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, negative 2, all the way across. And you can see that the log graph is the inverse. It is reflected off the line y equals x of the exponential graph. Any questions on that so far? All right, let's keep moving on. So you have seen another basic graph now that you want to remember so that you can apply all the transformations rules to. The logarithmic graph you want to think about in terms of how we developed it from the exponential graph. So let's just write down what we know. An exponential graph. What is the one point? So if you're thinking about like y equals a to the x, what is the point that always exists on an exponential graph? Yes, 0, 1, and goes up. So the point will always pass through 0, 1. And what's the asymptote of an exponential graph? Y equals 0. Good. And then the logarithm graph, since it's the inverse of the exponential graph, so we would look at this as log base a of y equals, wait a minute, not, I'm trying to think of in terms of the variable. Let's just write down what point would come here, and then I'll think about the variables that would match up with that. So instead of having 0, 1, what will always exist on your logarithm graph? 1, 0, good. 1, 0, so the point will always pass through 1, 0. And then we know that it's going to approach a vertical asymptote of 0, and then kind of look shaped in that way. So the asymptote will be at, instead of y equals 0, x equals 0. And I can't think of what the variables would be that would be the logarithmic graph. Don't know why I can't think of that. I'll come back to that. But this is the general shape that you want to think of for a log graph. All right. Would it be log base? It wouldn't be log base a because that would be equivalent to that. Log base, yeah. Okay, because if we plugged in the point 1, 0 for x and y, log base a of 1 has to equal 0. Yes, that's exactly right. So yes, thank you. I don't know why my mind was blanking on that. Okay, the next thing we really want to confirm what the log graphs look like. So take out your graphing calculator, and we're going to see how you can graph a logarithm graph. Log base 2 of x or log base 3 of x, both of them should have the point 1, 0. And then if you're doing just a sketch, I don't care how high or low each graph goes, but if you were doing actual points within a table, and you will be asked to do both based off of, even in your homework, there's 2 different ways that you're asked. So a sketch for log base 2 of x would just have to have the point 1, 0 and look like this. But an actual graph would have to have accurate points. So, and I would ask for just 3. So once you have the point 1, 0, that's fine. But what would be another good point to plot? 2, 1, excellent. Because when you have log base 2 of 2, the answer comes out to be 1. And then what would be another good point to graph? You could do 4, 2. Yep. 1, 2, 3, 4, 2. Or you could do 1/2 -1. And that would be a more accurate shaped graph. How about log base 3 of x? What would be good points to have other than 1, 0? What happens when x is 3? Yeah, 3, 1. And unfortunately, I can't show any more on this graph. But what happens when x is 1/3? Becomes -1. And we have that graph shown. Okay, with your partner, go ahead and graph log base 7 of x and log base e of x. This you can just sketch. You don't need exact points. But go ahead and sketch those two.
So, I'm assuming this will be on the quiz next Tuesday, and will this be on the calculator?
If I ask you, actually it could be on either. It could be on the calculator or non-calculator, because you should be able to plot in numbers in your head at this point, and you should be able to know how to sketch it. Hey guys, what if I had asked to graph the accurate y equals ln of x? What would be a good, like if we think about tables, other than 1, 0, what would be a good number to plug into your table? E, right? Because if I take natural log of e, what should I get back out? Let's think this through. What is ln of e, which is the same thing as log base e of e? 1. We did that one up at the top with a review of the notes. Log base e of e is equivalent to 1. So what is the value of e? Just kind of bringing it back from what we learned. 2.718. So I would go over to 2, close to 3, and plot that at 1. Or I could plug in a value like if I plug in 1 over e. If I think about 1 over e, you would think about it in terms of natural log of e to the negative first power. So what would be e to the negative first power? Or I'm sorry, what would this come out to equal? -1. So just things to think through. In your homework tonight, you're going to have to be able to do both, graph at a table and graph using just a sketch. So if you were looking at a table, you would want to make sure to show, well, let's see, 1 over e, that would be like 1 over 2. So 1 over 2.718, so at about 1/3, you would want to show -1. But the nice thing is, as long as you know the generic shape, you should be able to have a good idea of where the graph should end up. Okay, what do you notice about all of the graphs, regardless of if you sketched or if you used a table? They all have a basic shape. Yep, they all look like this. So that's a shape to memorize. And they contain what point? Yes, they all contain the point 1, 0. And they all, if you have a basic shape, they are approaching the x-axis. Therefore, they have a vertical asymptote at x equals 0. Any questions on that so far? All right, last but not least, let's just go ahead and sketch. So really this word, I'm sorry, I meant to cross it off and just say sketch. Graph means accurate, sketch means just the generic shape. So sketch the following without a calculator using what you know about transformations. Log base 3 of x plus 1, where x, the plus 1 is in parentheses. How would that move the graph? Yes, left 1 unit. So instead of having the basic shape at 1, 0 and kind of going up like this, I would need to move it to the left one. So where does that 0.10 move to? 0, 0. And now what are all of your points approaching? They're no longer approaching x equals 0. Yes, they're approaching x equals -1. So if we just kind of think through this, what would the domain be of this graph? Somebody said it. What'd you say, Olivia? Yes, -1 to infinity. What would the range be? -infinity to infinity. And then what would the vertical asymptote be? X equals -1. Good. Okay, let's do one more, we'll do two more together, and then I'll have you think through the last three on your own. Letter B. Okay, what happens with these transformations? What does the -2 do on the inside of the parentheses? Right 2 units. And what does the +3 do? Up 3. So if I'm thinking about the generic shape of a log, which goes through 1, 0, I now have to move this point right 2, 1, 2, and up 3, 1, 2, 3. So now it's here, and I know it continues the shape. But where are all of the values approaching now? They're approaching 2. Because we moved right 2 units. It doesn't matter how far up or down you go, but now what is the new vertical asymptote at? Careful, a lot of you are saying 2. Good, x equals 2. We want to make sure we know if it's y equals or x equals. Okay, what would the domain be?
2.
Yep. Parentheses 2 to infinity. What would the range be? Good, -infinity to infinity. The range will always be, yeah. Just like in an exponential function, the domain was always -infinity to infinity. Good. Unless you have it, like if you had it in the denominator of a rational function. That'll probably come in pre-calculus. All right, letter C. Letter C, what are the changes here? What does the negative on the inside of the parentheses do? Which way? Reflect over. Good, the y-axis. What does the +1 do? Move it up 1. So if I think about the generic shape through 1, 0, do your reflection first. So I'm going to reflect over the y-axis. So now it's going to move over here, this direction, but then also up 1. So where will the point 1, 0 move to? -1, 0, and then up 1. So where would that go? -1, 1. What would all of the values, so I know it's going to continue in this way, and then what are all of the values approaching? 0. If you're wondering when will my vertical asymptote change, your vertical asymptote changes based off of your left or right shifts. So if you have no left or right shift, then your vertical asymptote will not change. Okay, what would be the domain of letter C? What would the domain be? -infinity to 0. What would the range be? -infinity to infinity. And what's the vertical asymptote at? X equals 0. Good. Okay, take a minute to do D, E, and F with your partner, and then we'll check our answers up at the screen. Do list out the domain, the range, and the vertical asymptote as well.
I think it's a question over the x. So y.
Ah, shucks. Alright guys, check to see that you got letter D. Letter D, you should have it moved over the x-axis, left 2, down 3. So you should have domain -2 to infinity, range -infinity to infinity, and vertical asymptote x equals -2. The filled out notes to these are online. I'm sorry that 4.2 was not, but these are already up there. So you can check the other two as well.
I don't know